Turing in the Shadows of Nobel and Abel, an algorithmic story behind two recent prizes. I'm Dr. Samuel Alan Alexander, mathematician and philosopher, still here, and I'm going to be reading this article published in the Notices of the AMS in 2025 by David Gamarnik. Let's get started. The 2021 Nobel Prize in Physics was awarded to Giorgio Parisi for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales, and the 2024 Abel Prize in Mathematics was awarded to Michel Talleyrand for his groundbreaking contributions to probability theory and functional analysis, with outstanding applications in mathematical physics and statistics. What remains largely absent in the popular descriptions of these prizes, however, is the profound contributions the works of both individuals have had to the field of algorithms and computation. The ideas first developed by Parisi and his collaborators, relying on remarkably precise physics intuition, and later confirmed by Talleyrand and others by no less remarkable mathematical techniques, have revolutionized the way we think algorithmically about optimization problems involving randomness. This is true both in terms of the existence of fast algorithms for some optimization problems, but also in terms of our persistent failures of finding such algorithms for some other optimization problems. The goal of this article is to highlight these developments and explain how the ideas pioneered by Parisi and Talleyrand have led to a remarkably precise characterization of which optimization problems admit fast algorithms versus those which do not, and furthermore to explain why this characterization holds true. Section 1. Optimization of random structures. The works of Parisi and Talleyrand, which were devoted to understanding a mysterious object in statistical physics known as spin glass, offered an entirely novel way of understanding algorithmic successes and failures in tackling optimization problems involving randomness. This progress was propelled by understanding the physics properties of the underlying problems, namely the geometry of the solution space. We will illustrate these notions using three examples, all of which fit into a general framework of optimization problems of the form eta optimization equals with a delta over it, max sigma in big theta, big H of sigma calar. Here, big H is the function to be maximized, which we call the Hamiltonian for reasons to be explained later. Big theta is the space of potential solutions, and calar is a random variable describing the source of randomness. I wish you would explain what the equality with the delta over it means. Our three examples all exhibit a persistent computation to optimization gap, namely a gap between the optimal value, eta optimal, and the best guaranteed value that can be computed by known efficient algorithms, where efficient means polynomial time in the parlance of the theory of computational complexity. Example 1. Largest cliques and independent sets in random graphs. The first of our three examples is the problem of finding a largest clique in a dense Erdős-Rényi graph and the related problem of finding a largest independent set in a sparse Erdős-Rényi graph. Imagine a club with n members where every pair of members are friends or non-friends with equal likelihood 1/2, independently across all n choose 2 member pairs. What is the size of the largest group of members who are all friends with each other? This quantity is known as the clique number of the graph, whose nodes are the members and whose edges correspond to the pairs of friends. This club of random friends pairings is just a vernacular description of a model of random graph known as an Erdős-Rényi graph, denoted blackboard bold G of n 1/2. Paul Erdős introduced this model in 1948 as a very effective tool to study and solve problems in the field of extremal combinatorics. The question of estimating the largest clique size of an Erdős-Rényi graph was solved successfully in the 1970s, so like 20 years later, and has a remarkably precise answer with high probability, namely with probability approaching 1 as n goes to infinity, denoted as WHP with high probability. The size is 2 times 1 plus little o of 1, quantity times log 2 of n. Here little o of 1 denotes a term which converges to 0 as n goes to infinity. This is an instance of our optimization problem in which big theta is the set of all subsets of the node set bracket n equals the set 1 through n of the graph. Calar is the random graph itself, and big H of sigma calar is the cardinality of sigma when sigma is a clique of calar and big H equals 0 otherwise. The asymptotic value, 2 times 1 plus little o of 1 quantity log 2 of n, has a very simple intuition. Fix an integer value x and let z of x denote a random variable corresponding to the number of subsets of the set 1 through n which have cardinality x and are cliques. By the linearity of expectation, the expected value of this random variable is n choose x times 1/2 to the power x choose 2. By straightforward computation, this quantity converges to 0 when x is asymptotically larger than 2 log 2 of n, which provides a simple proof of the upper bound. The matching lower bound requires more work involving estimation of the variance of z of x, which is now standard material in many textbooks on random graphs. What about the problem of efficiently finding the largest clique algorithmically in at most polynomial time when the graph is given to the algorithm designer as an input? Here and elsewhere, we adhere to the gold standard of algorithmic efficiency when requiring that the running time of the algorithm grows at most polynomially in the size of the input. That is, we require that the algorithm belongs to Cal P, the class of algorithms whose running time grows at most polynomially in the size of the problem description, which in our case means it grows at most polynomially in n. Note that the largest clique problem can be trivially solved in time n to the power big O of log n by checking all subsets with cardinality 2 times 1 plus little o of 1 quantity log 2 of n. This growth rate is superpolynomial, and thus this exhaustive search algorithm is not in Cal P. This is where our story begins. In 1976, Richard Karp, one of the founding fathers of the modern algorithmic complexity theory, presented a very simple algorithm that computes a clique whose size is guaranteed to be roughly half optimal, namely 1 plus little o of 1 quantity log 2 of n. Given that his algorithm was not particularly clever, Karp challenged the community to produce an algorithm with a better performance guarantee with the stipulation that the algorithm still remain polynomial time. Remarkably, in the almost 50 years since the problem was introduced, there has been no successful improvement of Karp's rather naive algorithm, including, notably, the algorithm based on Markov chain Monte Carlo updates as shown by Jerome in 1992. This persistent failure further motivated Jerome to introduce one of the most widely studied problems in random structures and high-dimensional statistics, namely the infamous hidden clique problem. The problem of finding large cliques in the Erdős-Rényi graph with parameters n 1/2 thus exhibits a computation to optimization gap. Notably, while improving the half-optimality for the clique problem appears algorithmically hard, this hardness is only evidential, but not, at least not yet, formal. Namely, we do not have any proof of even conditional algorithmic hardness for this problem, say by assuming the validity of the polynomials not NP conjecture. This is in stark contrast with the worst-case setup. Namely, consider the problem of finding the largest clique for an arbitrary graph, in particular for graphs which are not necessarily generated according to the Erdős-Rényi n 1/2 distribution. For this version of the problem, it's known that no polynomial time algorithm can produce a clique within any multiplicative factor n to the 1 minus epsilon from optimality, in particular much larger than factor 1/2, unless p is not np. We see that in particular the half-optimality gap emerging in the random case does not align with the classic algorithmic complexity theory based on the p not equal to np conjecture. A very similar story takes place when the underlying model is a sparse random graph defined next. Fix a constant d. Consider a random graph denoted by blackboard bold g of n, d over n, so it's Erdős-Rényi with parameters n and d over n, in which every pair of nodes is an edge with probability d over n, independently across all pairs. We now switch to the mirror image of the clique problem, known as the independent set problem, defined as follows. A subset of nodes, big I, subset the set 1 through n, is called an independent set if it contains no edges. Namely, for all ij in big I, the pair ij is not an edge. Fries proved that the size of the largest independent set is eta sub d opt equals with the delta over it 2 times 1 plus little o sub d of 1 quantity log d over dn with high probability as n goes to infinity, where here little o sub d of 1 denotes a constant vanishing in d as d increases. Note, since there's two variables d and n, that necessitates distinguishing when we're writing the little o notation. Consider now the problem of identifying the largest independent set algorithmically in polynomial time. Using the formalism described in reference 1, big theta is the set of all subsets of the node set, the set of 1 through n, of the graph. Cal r is the random graph, the Erdős-Rényi n, d over n itself, and big H of sigma CalR is the cardinality of sigma when sigma is an independent set in the Erdős-Cheney graph, and big H equals 0 otherwise. An algorithm similar to Karp's-Clique algorithm computes an independent set whose size is roughly half optimal, namely 1 plus little o d of 1 quantity log d over d n, also with high probability. No improvement of this algorithm is known, and no formal hardness is known either. Thus, this problem is also evidentially hard and exhibits a computation to optimization gap. Example 2. Ground states of spin glasses. What's a spin glass? I never said I was a physicist. Our second example is in fact a probabilistic model of spin glasses themselves. Consider a tensor of random variables j equals big J sub I1 dot 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 IP, 1 less than or equal to I, 1 less than I2 less dot 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 less IP less than or equal to n, in reals to the n tensor P, where each entry big J I1 dot 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 IP of the tensor has a standard numerical distribution and all entries are probabilistically independent. The optimization problem of interest is eta np equals with a delta over it max sigma in the set minus 1 to the n to the minus p plus 1 over 2 times left angle big J sigma to the tensor p wrangle, where for every sigma in the set minus 1 to the n, Langle big J sigma to the tensor p wrangle equals sum 1 less than or equal to I1 less I2 less dot 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 less IP less than or equal to n big J I1 dot 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 IP sigma I1 dot 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 sigma IP. The optimal solution sigma star of this problem, which is unique up to a sign flip, is called the ground state of the model using physics jargon, and the optimal value is called the ground state value. The normalization n to the minus p plus 1 over 2 is chosen for convenience, see below. In our formalism, big theta equals minus 1, 1 quantity to the n, CalR is the tensor big J, and big H of sigma CalR is the associated inner product. The special case p equals 2 corresponds to the well-known and widely studied Sherrington-Kirkpatrick model. Notice how the signs of big J I1, I2 impact the optimal choices for sigma I. When big J I1, I2 bigger than 0, sigma I1 and sigma I2 prefer to have the same sign so that the product big J I1, I2, sigma I1, sigma I2 is positive. On the other hand, when big J I1, I2 is less than 0, sigma I1 and sigma I2 prefer to have the opposite signs so that the product big J I1, I2, sigma I1, sigma I2 is again positive. What's the best arrangement of signs to sigma I which optimizes this trade-off? This is the core of the optimization problem, which turned out to be quite challenging. In 1980, Parisi solved optimization problem 2 by introducing a mathematically non-rigorous but remarkably powerful physics-style method called replica symmetry breaking, RSB. The importance of the replica symmetry breaking-based technique is hard to overstate. It is the method of choice for computing the ground state values and related quantities for complex statistical physics models. Parisi's solution of problem 2 is as follows. Let Cal U be the set of non-negative, non-decreasing, and right continuous functions mu on the closed interval from 0 to 1 satisfying integral 0 to 1 mu of t dt less infinity. Consider the solution big psi mu of tx, with tx in the half-closed on the left interval from 0 to 1 cross the reals, of the following PDE with boundary conditions psi of 1x equals abs x, partial with respect to t big psi mu equals minus p times p minus 1 quantity over 2 t to the p minus 2 times partial squared x big psi mu plus mu of partial x big psi quantity squared. Define cal p of mu equals big psi mu of 0, 0 minus p times p minus 1 quantity over 2 integral 0 to 1 t to the p minus 2 mu of t dt. Theorem, for every p, the ground state value satisfies limit over n of a to p n equals infimum mu in cal u, cal p of mu equals with a delta over it, a to p opt, with high probability as n goes to infinity. The optimal solution, mu p opt, of the variational problem above is known to be unique and defines a cumulative distribution function of a probability measure, which has been called since then the Parisi measure. The identity in 4, that is, lim over n a to p n equals infimum mu in cal u, cal p of mu equals with a delta over a to p opt, was derived by Parisi heuristically using the replica symmetry breaking method. It was turned into a theorem by Talleyrand in 2006 in his breakthrough paper. Thus, one could say that the scientific value of the formula is worthy of 2 major prizes. Talleyrand's approach relied on a powerful interpolation bound developed earlier by Guerra. What about logarithms? Here the goal is to find a solution sigma such that n to the power minus p plus 1 over 2 times Langle big J sigma to the tensor p is as close to eta p opt as possible when the tensor big J is given as an input. Interestingly, major progress on this question was achieved only very recently, and it deserves a separate discussion found in section 5. Jumping ahead, though, the summary of the state-of-the-art algorithms is as follows. For p equals 2, near optimum solutions can be found by polynomial time algorithm. On the other hand, when p bigger than 2, this is evidently not the case. When he says evidently, I wonder if he means that we know it's not the case or just that it seems not the case. In summary, the largest value, eta p alg, achievable by known polytime algorithms satisfies eta 2 alg equals eta 2 opt, eta p alg less than eta p opt, p bigger than 2. Thus, similarly to example 1, the model exhibits a computation to optimization gap between the optimal values and the values found by the best known polynomial time algorithms. Example 3, satisfiability of a random k-sat formula. A third example, the final family of examples, consists of randomly generated constraint satisfaction problems, specifically the so-called random k-sat problem. An instance of a k-sat model is described by n Boolean variables x1 variables with values 0 or 1, and a conjunction big phi equals to the delta over it wedge 1 less than or equal to j less than or equal to m big Cj of m Boolean functions big C1 big Cm, each of which is a disjunction of precisely k variables from the list x1 xn or their negation. Here's an example for n equals 10 and k equals 3, big phi equals x3 or not x7 or not x8 quantity, and not x1 or not x2 or x7 quantity, and not x3 or not x7 or not x9. An assignment of variables x1 xn to values 0 and 1 is called a satisfying assignment if big phi equals 1 under this assignment. For example, the assignment x2 equals 0, x3 equals 1, x9 equals 0, and any assignment for the remaining xi's is a satisfying assignment for that example. The formula big phi is called satisfiable if there exists at least one satisfying assignment, and is called non-satisfiable otherwise. A random k-sat formula is generated according to the following probabilistic construction. For each j equals 1 through m independently across j, we select k variables xj1 xjk uniformly at random from x1 xn and attach the negation sign to each of them with probability 1/2, also independently across j equals 1 through m and small k equals 1 through big K. What's the small k? Did I miss where the small k occurs? That must be a typo or something. The resulting formula phi nm is a random formula whose probability distribution depends on n and m only. In the context of optimization problem 1, big theta equals the set 0, 1 to the n, cal r is the description of the formula big phi nm, and big H of sigma cal r is the number of clauses satisfiable by the assignment sigma in big theta. In particular, the formula is satisfiable if and only if max sigma big H of sigma cal r equals m. Whether or not big phi nm is satisfiable or not is now an event, which we write symbolically as big phi nm in sat. The probability of this event, probability big phi nm in sat, is our focus. There exists a conjectural critical threshold ck sat such that limit of n of probability of big phi n cn in sat equals 1 when c less ck sat and equals 0 when c bigger than ck sat. Informally, ck sat represents the largest fraction of clauses to variables for which the solution exists with high probability asymptotically in n. The existence of such a threshold ck sat was recently proven for large enough k. The constant ck sat has a very simple asymptotic expansion for large k. Ck sat equals 2 to the k log 2 times 1 plus little o k of 1, where little o k of 1 hides a function vanishing to 0 as k goes to infinity. We've seen that log of 2 times 1 plus little o of 1 before, haven't we? The intuition for this asymptotics is rather straightforward. Observe that any fixed assignment of xi, 1 less than or equal to I less than or equal to n, is satisfiable with probability 1 minus 1/2 to the k quantity all to the m. Thus, the expected number of satisfying solutions is 2 to the n times the mth power of 1 minus 1/2 to the k. The value 2 to the k log 2 is precisely the critical value of c at which this expectation drops from exponential of big theta of n, exponentially large, to exponential of minus big theta of n, exponentially small. Turning to algorithms, the best known one succeeds in finding a satisfying assignment only when c less than or equal to c0, 2 to the k log k over k, which is equal to the delta over ck alg. Here c0 denotes a universal constant. Namely, The best known algorithm succeeds only when the clause to variable's density is nearly a factor k over log k, exclamation mark, smaller than the density for which the solutions are guaranteed to exist with high probability. This is an even more dramatic gap than the half-optimality gap seen earlier for cliques/independent sets in the Erdős-Rényi n1/2 and Erdős-Rényi n d over n models. Random k-set is thus another instantiation of the computation to optimization gap similar to the ones found in examples 1 and 2. In the remainder of the article, we will explain the nature of these gaps. In particular, we will explain the values 1/2 eta p alg and ck sat by leveraging powerful ideas first developed toward understanding statistical physics of materials called spin glasses. An interesting bridge between math and physics. Physics matters. Spin glasses. Presumably they're not talking about the kind of glasses you wear on your eyes. Statistical physics studies properties of matter using probabilistic models which provide statistical likelihoods one finds physical systems in different states. These likelihoods, in their turn, are linked with the energy of these states. As the energy decreases, the likelihood increases. One can apply this viewpoint to our optimization problem, max sigma big H of sigma dot, thinking of big H of sigma dot as negative energy, Hamiltonian, of the state sigma. The ground state is then a state with the lowest energy. The link between energies and likelihoods is formalized by introducing the Gibbs measure on the state space big theta, which assigns probability measure Langle sigma wrangle equals z to the minus 1 exponential of beta big H of sigma dot to each configuration sigma. Here z is the normalizing constant called the partition function. The parameter beta is called inverse temperature. At low temperature, namely large values of beta, the Gibbs measure becomes concentrated in near ground states, states with nearly the lowest energy. The identity in equation 4, which is way above, was first derived for the case of finite beta and then extended to the case beta equals infinity, corresponding to the ground state value. The added value of introducing the Gibbs measure is that it allows one to consider the entire space big theta of solutions in one shot, where the solutions are stratified by their energy levels. This is the so-called solution space geometry approach, which turned out to be very fruitful for the analysis of algorithms. Spin glasses are particularly complex examples of matters which exhibit properties of being liquid and solid at the same time. For a recent treatment of the subject, see reference CMM plus 23. Mathematically, spin glasses correspond to the fact that the associated Hamiltonian big H, which is the sum j big Hj of many local Hamiltonians, representing interactions of nearby atoms, is frustrated. Put differently, it is impossible to find a spin configuration sigma which simultaneously minimizes the energy of each component big Hj. This makes it very similar to problems we've considered in our examples. The idea of repurposing the technique from the theory of spin glasses for the field of optimizations of combinatorial structures goes back to the mid-1980s, around when I was born. In particular, Fu and Anderson in their 1986 paper Application of Statistical Mechanics to NP-complete Problems in Combinatorial Optimization say, "We propose to study the general properties of such problems, combinatorial optimization, in the light of the structure of solution space, the existence and the nature of phase transitions." Section 3, Clustering Phase Transition in Random K-set. The first fruitful and mathematically verified link between the solution space geometry and phase transition on the one hand and the algorithmic tractability hardness on the other hand appeared in concurrent works of Ekleoptas and Ricci-Tersengi and Mezard-Mora and Zecchina in the context of the random K-set model introduced earlier. Given a random formula big phi nm, let sat nm subset the set 0, 1 to the n denote the random set of satisfying assignments. RSB calculations, which were originally introduced to study spin glasses, suggest heuristically that the bulk of this space should be highly clustered at some large enough clause density C less ck sat. This is what these papers established in a mathematically rigorous way. In particular, they prove the following theorem. For every k bigger than or equal to 8, there exists ck clust less than ck sat, such that the following holds when C in the open interval from ck clust to ck sat. With high probability, as n goes to infinity, there exists a disjoint partition sat nm equals union over L, sat L, quantity union sat O, L bigger than or equal to 2, such that the Hamming distance between any two distinct sets sat L1 and sat L2, with L1 not equal to L2, is big omega of n, and the cardinality of sat O over the cardinality of sat nm equals exponential of minus big omega of n. This is illustrated in figure 1. The authors argued that the presence of such a clustering picture suggests algorithmic hardness of finding satisfying assignments, in particular by means of some local search type algorithms. Figure 1. clustering phase transitions at alpha clust approximately alpha alg. Below alpha clust, a bulk of the solution space, blue, is a giant connected set. Above alpha clust, a bulk of the set is partitioned into blue clusters with exponentially small exceptions in gray. Furthermore, as subsequent work showed, intriguingly, the onset of this clustering property phase transition coincides with the evidential algorithmic hardness discussed earlier asymptotically as k. More precisely, it was verified that ck clust equals 1 plus little o k of 1 quantity times 2 to the k log k over k equals 1 plus little o k of 1 quantity ck alg. This was the first, though purely hypothetical, link between the solution space geometry and the algorithmic hardness. Very quickly, similar result was established also for the independent set problem in Erdős-Renyi n d over n and several other similar problems. For all c in the open interval from 1 to 2, independent sets of size c times 1 plus little o d of 1 quantity log d over d, and notice the typo, there's a missing right parentheses, namely more than half optimum, are clustered, and for all c in the open interval from 0 to 1, they are not clustered. What about the clustering property in spin glasses? It does take place, and this is in fact what originally prompted Parisi to develop his RSB approach. Clustering in spin glasses is more intricate and comes in the form of a nested hierarchy of subclusters arranged in a particular way called an ultrametric tree. Ah, so this actually touches a little bit on mathematical logic, in an indirect sort of way. We delay the discussion of this structure until section 5 when we discuss how this ultrametric structure of clusters successfully guided the creation of the state-of-the-art algorithm for problem 2. Section 4. Overlap gap property, a provable barrier to algorithms. As discussed earlier, the clustering property exhibited by random k-set and similar other problems provided, unfortunately, only a hypothetical explanation of the algorithmic hardness, but not a proof of it. The property, which turned out to be a provable barrier to algorithms, was inspired by the clustering picture, but came in the different form of the overlap gap property, OGP, which we now formally introduce in the context of problem 1. For this purpose, we assume that the solution space big theta is equipped with some metric d, for example, Hamming distance when big theta is a binary cube. Definition. An instance big H of .cal R of optimization problems exhibits a overlap gap property with parameters eta overlap gap property less than or equal to eta overlap gap property eta overlap gap property less than or equal to eta opt with nu1 less nu2 if for every sigma tau in big theta satisfying big H of sigma clar, big H of tau clar bigger than or equal to eta overlap gap property, it holds that the distance from sigma to tau is not in the open interval from nu1 to nu2. This property has a simple interpretation. The model exhibits the overlap gap property if the distance between every pair of near optimal solutions with values at least eta overlap gap property, is either small, has a high overlap represented by distance sigma tau less than or equal to nu1, or is large, has a low overlap represented by distance from sigma to tau bigger than or equal to nu2. We need to extend definition 4.1 in two ways, first involving the ensembles of instances CalR1 CalRm, and second involving overlaps of more than two solutions. Definition. Fix a positive integer big M and a subset nu subset big theta to the big M. A family of problem instances CalR1 CalR big T exhibits an overlap gap property with parameters eta overlap gap property nu if for every 1 less than or equal to L1 less than or equal to L2 less than or equal to less than or equal to L big M less than or equal to big T, and every sigma 1 sigma big M in big theta satisfying big H of sigma 1 cal R L1 big H of sigma big M cal R L big M bigger than or equal to eta overlap gap property. It holds that sigma 1 sigma big M not in nu. Definition. Definition 4.1 is recovered as a special case when big T equals 1, big M equals 2, and big theta squared superset nu equals the set of pairs sigma tau such that the distance from sigma to tau is in the open interval from nu1 to nu2. We stress that the randomness CalR appearing in big H of sigma j CalR Lj is index specific, representing the fact that sigma j is near optimal, achieves a value of at least eta overlap gap property, specifically for instance CalR Lj. While the intuition behind the definition is fairly direct, the one for the second definition is rather opaque and requires some elaboration to be done shortly. It turns out that the overlap gap property does hold in our models and is a provable obstruction to classes of algorithms. The first of these facts, in the context of the first definition, was already implicitly established in the reference ART06 and the reference MMZ05 as a method for proving the clustering property for the random k-set model. The fact, though, that the overlap gap property is a provable obstruction to algorithms was established first in 2017 in the context of independent sets in sparse Erdős-Renyi graphs searchable by local algorithms. Loosely speaking, an algorithm is local if for each node I in the set 1 through n, the decision to include it into an independent set is conducted entirely based on a constant size graph theoretic neighborhood around I, simultaneously for all I, ignoring the rest of the graph. The result in 2017 says the following. Theorem. For every epsilon bigger than 0 and sufficiently large d, there exists 0 less nu 1 less nu 2 less 1, such that with high probability as n goes to infinity, the set of independent sets in Erdős-Rényi n d over n exhibits an overlap gap property in the sense of definition 4.1 with parameters eta overlap gap property equals to the delta over it 1/2 plus 1 over 2 radical 2 plus epsilon quantity eta d opt semicolon nu 1 n comma nu 2 n. As a result, no local algorithm appropriately defined exists for constructing an independent set with size larger than eta overlap gap property. Namely, every two independent sets with cardinality, which is multiplicative factor 1/2 plus 1 over 2 radical 2 close to optimality, are either at a small distance from each other, at most eta 1n, or a large distance from each other, at least eta 2n, at least nu 2n. Theorem 4.3 means that beating a factor 1/2 plus 1 over 2 radical 2 optimality threshold for this problem will require going beyond the class of local algorithms. Local algorithms do, in fact, achieve half optimality, which we recall as the evidential barrier for this problem. The gap between half optimality and 1/2 plus 1 over 2 radical 2 was eliminated in 2017 with the same class of local algorithms and later for a larger class of algorithms. This was achieved by turning to multi-overlaps of solutions and resorting to definition 4.2. A method to adjust broader classes of algorithms requires interpolating between instances, that is, having big T bigger than or equal to 2 in definition 4.2 as was introduced in 2019. The broadest currently known class of algorithms ruled out by the overlap gap property is the class of stable noise-insensitive algorithms. We will not give one informal definition of this class as it comes in different context-dependent variants. Loosely speaking, the stability property means the following. We think of an algorithm as a map alg calar to big theta, which maps instances calar of random inputs, graphs, tensors, etc., to solutions. We say that the algorithm alg is stable if a small perturbation of the input calar results in a small perturbation of the solution alg of calar. Namely, if calar approximately calar prime, then alg of calar approximately alg of calar prime. A local algorithm is an example of a stable algorithm. Deleting or adding one edge of a graph will affect the decisions associated only with nodes which contain this edge in their constant size neighborhood. This is so because the algorithm performs these decisions concurrently, in parallel. Thus, deleting or adding one edge changes the independent set produced by an algorithm and at most may go of one many nodes. Other classes of algorithms proven to be successful for these types of problems, including approximate message passing, stochastic localizations, low-degree polynomials, and Boolean circuits with small depth, turn out to be stable as well. It was established in a series of follow-up works that the overlap gap property is a barrier to stable algorithms. For our problems outlined as examples 1 and 3, it provides tight algorithmic bounds as described in the following theorem, stated informally. The sequence of interpolated instances involving these examples is constructed as follows. For example 1, involving sparse random graph Erdős-Rényi n d over n, consider any ordering copy of pairs ij, 1 less than or equal to I less j less than or equal to n, and consider the process of free sampling each edge according to the same Bernoulli distribution with values 1, 0 with probabilities d over n, 1 minus d over n, respectively, one pair at a time according to the order cal p. At each step t, we obtain a random graph, blackboard bold gt, which is distributionally identical to Erdős-Rényi n d over n. After big T equals n choose 2 steps, we obtain a fresh copy of Erdős-Rényi n d over n, which is probabilistically independent from the starting copy. This is our interpolated sequence calar1 calar big T in the context of example 1. It is constructed similarly for the case of random k-set example 3. Theorem. For every large enough D, there exists a large enough big M and a subset nu such that with high probability the set of independent sets in the interpolation sequence blackboard bold gt 0 less than or equal to t less than or equal to big T equals n choose 2 of graphs Erdős-Rényi n d over n exhibits an overlap gap property with parameters eta overlap gap property equals 1/2 1 plus little o d of 1 and nu. As a result, the largest independent set which can be constructed by stable algorithms is asymptotically eta overlap gap property equals 1/2 1 plus little o d of 1. Similarly, for every large enough big K, there exists a large enough big M and a subset nu such that with high probability the set satisfying assignments in the interpolation sequence big phi t of a random K set formula big phi n alpha n exhibits an overlap gap property with parameters eta overlap gap property equals eta opt and nu when alpha bigger than alpha K alg. As a result, the largest constraint to variables density for which stable algorithms can find a solution of a random k-set problem is alpha big K alg. In particular, in both cases, the overlap gap property provides a tight characterization of the power of stable algorithms. For the second part of the theorem, we set eta overlap gap property equals eta opt, since for constraint satisfaction problems there's no notion of approximation to optimality as we consider exclusively satisfying assignments. Variants of the theorem were proven in 2017 and 2022. Why is the overlap gap property a barrier to stable algorithms? The intuitive reason for this is a rather simple continuity type argument, and best illustrated in big K is equal to 2. And mu is of the form in equation 5, which was big theta squared superset nu equals the set of pairs sigma tau such that the distance from sigma to tau is in the open interval from nu1 to nu2. Suppose that in addition to the properties outlined in definition 4.2, two additional properties hold. First, the sequence of instances CalR1 ... CalR big T is continuous in the sense that CalR T approximately CalR T plus 1 for all T. Second, suppose that when L1 equals 1 and L big K equals L2 equals big T, the case distance from sigma 1 sigma to sigma 2 less than or equal to nu1 does not occur. Namely, while per definition 4.2 for every pair sigma T1 sigma T2 of solutions with values bigger than or equal to eta opt in the interpolated sequence CalR T equals 1 through big T, both D of sigma T1 sigma T2 less than or equal to nu1 small distance and bigger than or equal to nu2 large distance situations are possible. When the two solutions correspond to the beginning, that is T1 equals 1, and the end, that is T2 equals big T, of the interpolation sequence, only the latter situation, distance from sigma T1 to sigma T2 bigger than or equal to nu2, large distance, is possible. This can indeed be established in many special cases using the same techniques which verified the overlap gap property. Then the argument establishing the overlap gap property as an obstruction to stable algorithms goes informally as follows. Consider implementing a stable algorithm alg on a sequence of interpolated instances CalR T, 1 less than or equal to T less than or equal to big T, resulting in a series of solutions alg of CalR T. Since the sequence CalR T is continuous, changes slowly as T increases, and the algorithm is stable, then the distance from alg of CalR1 to alg of CalR T changes continuously as well as T changes from its initial value. The distance from alg of CalR1 to alg of CalR1 equals 0 less than or equal to nu1 to its final value d of alg of CalR1 to alg of CalR big T, which by a property above must be bigger than or equal to nu2. For any T by the overlap gap property, we have distance from alg of CalR1 to alg of CalR T is either less than or equal to nu1 or bigger than or equal to nu2. Therefore, there must exist tau such that the distance from alg of CalR1 to alg of CalR T is less than or equal to nu1, and the distance from alg of CalR1 to alg of CalR T tau plus 1 bigger than or equal to nu2. Must exist tau. Did I say T? By the triangle inequality, this means the distance from alg of CalR tau to alg of CalR tau plus 1 is bigger than or equal to nu2 minus nu1. But this contradicts stability of alg. The argument is illustrated in Figure 2. Figure 2. Overlap gap property is an obstruction to stable algorithms. The algorithmic path, blue curve, that's the jagged curve on the right, has to jump, red section, from the small distance less than or equal to nu1 region to the large distance bigger than or equal to nu2 region in the space of solutions big theta. Recall now the clustering property discussed earlier. Could one build an algorithmic barrier type argument directly from the clustering property? It appears the answer is no, as evidenced in a different model called the symmetric binary perceptron model from 2022. In this model, which also involves constraints to variables parameter alpha, algorithms find a satisfying solution up to some value alpha alg bigger than 0, and an overlap gap property above alpha overlap gap property approximately alpha alg bigger than 0 is exhibited. Yet at the same time, the model exhibits clustering at every positive value alpha bigger than 0. It thus appears that geometric structures which are barriers to algorithms are more involved than clustering and have to rely on more complex structures such as multi-overlaps nu. We'll see this in an even more pronounced form in Section 6 in the context of spin glasses. Section 5. Ultrametricity guides algorithms for spin glasses. We now turn to the state-of-the-art algorithms for spin glasses, our example 2, specifically algorithms for solving optimization problem 1. A dramatic progress on this problem and a fairly complete understanding of its algorithmic tractability was achieved only recently in the works of Subag in 2021 in the context of related so-called spherical spin glass model, and of Montanari in 2019 in the context of precisely problem 1 in the special case p equals 2, namely the Sherrington-Kirkpatrick model. Montanari has constructed a polynomial time algorithm which achieves any desired proximity eta p opt minus epsilon to optimality with high probability, assuming an unproven though widely believed conjecture that the cumulative distribution function associated with the Parisi measure mu p opt solving variational problem 4 is strictly increasing within its support. Namely, the support of the measure induced by mu p opt is a connected subset of the closed interval from 0 to 1. We'll connect this property with the overlap gap property shortly. Soon afterward, the result was extended to general P in 2021, and a new algorithmic threshold, eta p alg less than or equal to eta p opt corresponding to the best known and stable algorithms was identified. This is summarized in Theorem 5.1 stated informally, Theorem 5.1 informal. Let cal L superset cal U be the set of functions on the closed interval from 0 to 1 with total variation appropriately bounded. Let eta p alg equals with the delta over infimum mu in cal L, cal P of mu less than or equal to eta p opt equals infimum mu in cal U, cal P of mu. There exists a polynomial time-stable algorithm which constructs a spin configuration sigma alg achieving approximately eta p alg with high probability as n goes to infinity. When p equals 2, it is conjectured that the variational problem infimum mu in cal L, cal P of mu is solved by a strictly increasing function, and thus modulo this conjecture Montanari's algorithm achieves near optimality. It is known, however, that this is not the case when p bigger than or equal to 4 and p is even. In this case, eta p alg equals infimum over mu in cal L, cal P of mu less than eta p opt equals infimum over mu in cal U of cal P of mu. We now explain the algorithmic threshold eta p alg and the successful algorithm for achieving it. The Parisi measure mu p opt is conjecturally a measure describing random overlaps of nearly optimal solutions in the following sense. Fix a positive inverse temperature parameter beta and consider sampling two spin configurations sigma 1, sigma 2 from the associated Gibbs measure independently. Then mu p opt is the distribution of the inner product overlap n to the minus 1 Langle sigma 1 sigma 2 wrangle in the limit beta goes to infinity. Furthermore, suppose instead m samples sigma j in the set from 1 to m are generated according to the same Gibbs distribution. Then the distribution of the set of overlaps n to the minus 1 Langle sigma j1 sigma j2 wrangle is believed to be described by distributions over a set of m values in the closed interval from 0 to 1 arranged on a tree. As such, it satisfies a strong form of the metric triangle inequality, with Max replacing the addition operator called ultrametricity, depicted in Figure 3. When the Parisi measure mu p opt is strictly increasing and there's no gap in its support, the branching points on the tree are located in a continuous way without gaps. It turns out that this coincides with the case infimum over mu in cal L cal P of mu equals infimum over mu in cal U cal P of mu, implying eta p alg equals eta p opt, and this is the case when the algorithm reaches near optimality. The algorithm is constructed as a walk in the interior of the nth power of the closed interval from minus 1 to 1, which starts from the center of the cube and follows the ultrametric tree as a guide. Specifically, at every stage, it makes a small incremental step in the direction which A, maximally improves the objective function, and B, orthogonal to the previous direction. Absence of gaps implies that the algorithm proceeds without interruption until hitting a corner of the nth power of the closed interval from minus 1 to 1, provably reaching near optimality. In a sense, the ultrametric tree guides the successive steps of the algorithm. Figure 3, ultrametric tree of solutions in the nth power of the closed interval from minus 1 to 1. End points of the curve correspond to corners of the cube. The Parisi measure has no gap in the support reflected in the tree branching continuously. When the Parisi measure is not strictly increasing, the authors show that the algorithm reaches the largest energy level achievable by ultrametric trees without gaps. This was shown to be the value of the extended variational problem infimum mu in cal L cal P of mu, which per equation 6 is strictly smaller than infimum mu in cal U of cal P of mu. Section 6. Branching overlap gap property, tight characterization of algorithmically solvable spin glasses. A final missing piece completing the algorithmic tractability versus hardness picture for spin glasses was delivered by Huang and Selke in 2022. When the Parisi measure mu p opt exhibits a gap in its support, and as a result we have strict inequality 6, this inequality can be turned into an obstruction to algorithms along the lines of theorems 4.3 and 4.4. Specifically, in the spirit of definition 4.2, that mu p gap by the set of big M tuples sigma j in the set from 1 to big M, subset big theta to the big M, such that the set of the associated overlaps n to the minus 1 Langle sigma j ij in the set from 1 to big M, represents a continuous branching tree in some precise sense, the kind we see in Figure 3. Then the model exhibits an overlap gap property above the value eta p alg, with nu serving as the multi-overlap obstruction. More specifically, we have the following theorem. Theorem optimization problem 2 exhibits an overlap gap property in the sense of definition 4.2 with parameters eta p overlap gap property equals to the delta over it eta p alg, comma, nu p gap. This property is an obstruction to stable algorithms in finding spin configurations with values larger than eta p alg with high probability as n goes to infinity. Hence, when combined with Theorem 5.1, eta p alg represents a tight algorithmic value achievable by stable algorithms. As a corollary, a p-spin model can be solved to optimality by stable algorithms when p equals 2 modulo the strict monotonicity conjecture discussed above. On the other hand, when p bigger than or equal to 4 is even, the largest value achievable by stable algorithms is strictly suboptimal. It is conjectured that this remains the case for all p bigger than or equal to 3 regardless of the parity, and has been verified for the case when p is sufficiently large. The multi-overlap gap property obstruction set nu p gap is called branching overlap gap property, or BOGP. It subsumes the obstruction sets nu appearing in the context of theorems 4.3 and 4.4 special cases, and it represents the most general known form of overlap gap property-based obstructions. The proof of the theorem follows a path similar to the one used in theorems 4.3 and 4.4 and is also based on the interpolation scheme between instances, using in a crucial way the approaches developed by Talleyrand in 2006 and earlier by Guerra in 2003. In particular, one creates an interpolation between many instances, big H dot big J, J, J in the set 1 through big M, of the Hamiltonian arranged in a particular tree like a continuous way. One then argues that a stable algorithm implemented on this continuous tree of instances results in a continuous due to stability tree of solutions, the kind represented in figure 3. Then a separate argument is used to show that every continuous tree of spin configurations, sigma j, j going from 1 to big M, will have at least one solution with energy at most 8p alg, and thus, using an additional concentration argument, stable algorithms cannot beat this threshold. Putting it differently, big M tuples of spin configurations achieving simultaneous values larger than eta p alg have associated altimetric trees with gaps, as represented by the red segments in figure 4. Figure 4 description altimetric tree of solutions when the Parisi measure has a gap in the support leading to gaps in branching locations. It is reasonable to believe that the scope of algorithms limited by the value eta p alg is much broader than the class of stable algorithms, and quite possibly includes the class of all polynomial time algorithms for these and similar problems. Such a result, however, is out of reach for now due to its very strong algorithmic complexity implications. That was a very interesting paper, totally over my head as usual, but we gain a lot of insight by reading it anyway. Please like, comment, and subscribe, and I'll see you in the next video.